Okay, so this is the introductions. So do you want to start?
Like my name.
Yeah, just your name and like majors, so we all know each other.
Name's Jessica. My major is biology, and I'm just here to support him. But yeah.
Yeah. Okay. We can move. Yep.
And there's Dominic in the second year. And I started to time.
My name's Andrea. I'm a second year and I'm a data science major.
My name's Nathan. I'm a fourth year and I'm a computer science major.
And I'm Ishan, I'm a second year and I'm also a CS major.
I'm Derek. I'm a second year CS major.
I'm Jonathan. I'm a third-year CS major. Yeah, and this is my workshop on state space models and MAMBA. So before we talk about state space models, I don't give a quick it's a disclaimer, okay? I'm not professional on this topic. I just like to read research papers for fun and show my interest and passion. So if I get anything wrong, don't you can call me out, but just don't look make fun of me, okay? This is all for fun, okay? So before getting into stasis model, I kind of want to give like a prereq in case like no one knows what a transformer is. So like a transformer is a deep learning architecture used for sequence-to-sequence tasks, such as machine translation, text. Hello, hello. Oh yeah.
I'm so sorry. I thought you were saying like
Nah. This is the president Carl Sack, by the way.
ex-president. Now I'm not president anymore.
My bad, ex-president. Okay.
Literally, now.
Okay. Yeah. So yeah, so the transformer, I'm gonna restart. Like it's a deep learning architecture used for sequence-to-sequence tasks, such as machine translation, text summarization, and a lot more things. And the two main components I kind of like you guys should kind of remember is an activation function and self-attention. So an activation function is pretty much decides whether a neuron should be activated or not. So this means I have to decide whether the neuron input to the network is important or not in the process of predicting prediction using simpler mathematical operations. You don't have to know exactly what this means, just remember the name, attention function. And the next one is self-attention, not activation function, sorry. Next one, self-attention. And that's pretty much the process of where each token in the input sequence is compared with every other token, allowing the model to focus on important parts of the input regardless of the position in the sequence. So pretty much transformers is what every single language model pretty much uses, like ChatGPT, Claude, etc. So this is like the main fundamental of machine learning that like makes up the whole space of predictions. But of course, even though it's so commonly used in every single language model, there is some limitations. So one of the main limitations is as a long sequence grow to a larger sequence, it can be less efficient due to the computation requirement of O n square, which could be also very computationally expensive. And this is an actual point from a real research paper, which says like transformers models trained on long sequence often achieve higher accuracy than a short sequence. Unfortunately, conventional transformers struggle with long sequence training due to the overwhelming computation and memory requirement. So if you guys want to look more into like the flaws of transformers, like current day, you can like read this paper between 23. So now that we know like what a transformer is and the limitations of it. Oh, by the way, yeah, this is how it usually looks like. You don't have to focus too much on this. But now we can get into now this is the actual present of curl stack. Okay, so now we can go into what state space model is. Okay, so a state space model is a mathematical model that describes dynamic system evolving over time. They use state variables to represent the system's current state and observe how the system changes over time. So the mathematical equation of this is an actual true equation that's used for many different things, but someone was able to kind of modify it in a way so it could be used within like machine learning and to predict stuff based on the current states and previous before it. And the key components of state space models are the state vectors, which captures the system's state at a given time, the observation vector, what we use to observe from systems at each time step, and the state transition defines how systems evolve and how observations are made. I will get a lot more deep into it, just but recognize the name, okay? In the mainstreams of it, it's very ideal for computational continuous time dependency systems, and it effectively captures how systems evolve over time. So what this means like it's calculated like linearly. So like instead of n squared like a transformer. It's just like an n, okay? It calculates over time. And that's the main benefit of it, okay? So I'm gonna go over the main equation. It's kind of split into two pieces, okay? The main piece is the x prime equals A matrix A times x plus B times C, okay? So x is the same as a state vector at time t. So this vector contains a variable that describes the system at a given time. So for example, this can represent the current position and velocity of the object. A is a state transition matrix. And this matrix defines how the current state x is influenced in the next state. So I can see this vector and this matrix are combined right here. B is a control input matrix. This matrix describes how the external input U influences the state, and U is the input of time t. So I can see, you can see my mouse, but like, they are all multiplied together, and when you add it, that will represent x prime, which is the derivative of this vector of the state vector. So this shows like the rate of change of the current state. I'm gonna show an example. Okay, I'm just so you guys have an idea. Okay, this is part one of the equation, and part two is a lot shorter, but y is the observation vector at time t. So like, pretty much the whole output. C is the observation matrix. This is a typo. This matrix defines how the external state x influence the observation y. And D, the input matrix, you can kind of ignore D because when I was researching things, every single YouTube video, every single research paper, they always ignore D. I don't know why, but I'm just ignore it also. Okay, so don't focus on D. Just focus on the Y and the C. Okay. Yes.
Like I'll give questions now, like after you finish.
If anyone has urgent
I have
questions.
like a small question, like,
Mhm.
what's the difference between like the X vector and like the observation vector essentially? Is the observation vector like the output of the
Yeah,
vector?
so the observation vector is pretty much the output of the whole thing once everything's calculated at that state.
Mhm.
But that might not make too much sense now, but I'm gonna show an image, so it makes a lot
Okay.
more sense, okay? So yeah, so there's an overall overview of it. So like I guess mentioned, let's move this in. The U is the vector of the input, and this will be multiplied by the input matrix, which is B. And then we also have X, which is the previous state that we're in it, and this will be multiplied by the state matrix A. So once we multiply these two, you add them up, and this will give you an output. And this output will be multiplied by the output matrix, and that will be your given Y. And you keep doing this like every single state you're in. So the state's like 100 states, those will run 100 times linearly, okay? I think in a more simple example of this is from a YouTube video. So it's a car example, okay? So you have a car at state T, okay? You have the input X multiplied by the matrix B. Then you get matrix A multiplied by the previous state, which is T minus one. Once you multiply these two, and you add it up, you multiply it by the output matrix C, and that will be you given output. Like I said, you can just ignore D. This is a more simplified version of two states, but like once it gets longer, um, once it gets longer, that's how it looks like. It could be like it could be 40 states, it could be 100 states, it could be forever. But this is pretty much how it goes. So like, and the main thing you guys should focus on is matrix A, because matrix A is what contains all the information. As you can see, like none of these are reused, but like A is used throughout the whole time. So once you get to A right here, it'll contain the information from all the previous states previously. So this is what makes it so good. Is it linearly, and we still can have the information from all the previous nodes or states. So I kind of like go through the equation again, but more as like a simplified example. So I'm gonna talk about a student's brain, okay? So the U is a control input at time t. And this represents the external factor that influences the student's learning. So an example, it could be I study 1 hour. So the 1 hour, that could be the input. B is the control input matrix. This can determine how external actions, such as practice, study times, or tutoring, affects the student's learning process. So I spend 2 hours every day studying, and this external input boosts my knowledge over time. So B would determine how impactful this input would be. X is the represents the student's knowledge at our current time. So this could be a score or understanding level of a test or quiz. So this can scale from 1 through 100%. Just how is a student, how smart is the student at this time so far? A is what pretty much the matrix that contains all the information from previously. The X prime is a rate of change of the student's knowledge over time. So are they improving? Are they not improving? The C is the observation matrix, which tells how the student's knowledge T is reflected in the observation Y. So how well a student's theoretical knowledge transitions to the actual quiz, and Y is the actual input, how they perform. Okay, so do you guys kind of understand the equation so far? Yeah, yeah.
I have a question about the equation. Is xt a vector or a scalar?
I think it would be either, but mostly in this example, it's a vector. But usually in inputs, you can have an input, a token, like one word, but like that word to be tokenized into a large vector of some sort. So it could be a scalar, but most times it should be a vector. Make sense? Okay. Now, but there's one issue with state-space models. They forget, okay? So they have the forgetting problem. So while state-space models are good for capturing state translation over time, they often suffer from forgetting important information, especially in complex systems or over a long period. So an example is imagine a student learning new material, and over time they might forget the order lessons. It's pretty much the same thing as state-space models. So like you guys might be confused, like I just clickbaited you. I said that stasis model is good because they remember long term, but they don't, okay? So that's why in 2023, two researchers, I think one is from Princeton, they made a modification on state-space models on how can we make this equation good that can possibly replace a transformer. And this is where we get into MAMBA, okay? So MAMBA stands for Memory Augmented Models for Brain-like Abstraction, and a memory augmented, long as name, model designed to address the forgetting problem in states. So this introduces the explicit memory model that stores important information for long-term retention, and it retains important past states while decreasing irrelevant details. I think this is the most important thing that makes MAMBA. When it's multiplying throughout the equation, it'll remember the important stuff, it'll increase the value of it, but the irrelevant stuff, it'll decrease it. So that A matrix will be actually like accurate and have information that we want. So this is based on a very popular research article that I read. Pretty complex. I don't understand like 9% of it, but like enough to make this workshop. So you guys are interested? Like I highly suggest reading this. It was actually a very popular article back when it came out. So yeah. So now that we've gone through this, now we get to the difficult part of Mamba. And it's pretty difficult. I didn't make any slides of it, okay? But this man named Martin with two A's for some reason, he actually made a whole article about Mamba with visuals. And that's what I want to go through with you because it makes it a lot more simpler than just making a workshop. So yeah, so like this is the guy who made this. So thank you, Martin. But yeah, so like as previously, this is what a normal state space model looks like. As you can see, the input multiplied by the matrix, you get the A multiplied by the past state, you add them up, and that'll be output, and it'll just keep going constantly. Yeah, so it's just a visual of it. And I gotta scroll it down a bit. And there's one way you can do SSMs, but another way is using a kernel. So for anyone who doesn't know what kernel is in a convolutional neural network, this is how you predict images and what they are. You can have an input like an image, and you have a kernel. And a kernel is pretty much a filter, an n by n filter that contains information. So let's just say you have an image of a dog, okay? And you want to grab information on where its nose is. So you can make a filter of that represents a nose. I think nose because like there's a dot right here. So pretend this kernel represents a nose. So it'll scan throughout this whole image and calculate it and for an output. And this output will contain it where the nose is of a dog. And while convolutional neural networks, they have multiple kernel filters for every single feature that you want. And this someone modified an SSM equation. So it's kind of similar to this. So how they did it is instead of having like a n by n filter, you have a 1D vector, a 1D filter of it. So let's say we have the input. Hello, my name is blah blah blah. This kernel can predict once it scans throughout the whole input, it can predict what the next word is. So I can see this kernel scans through my name is. This could be like some sort of like equation. It could be like non-error. It's up to you. It's just a filter. And this will predict the output, which is Martin. So knowing what a kernel filter is, someone, yep,
Yeah, quick question. So like, can you scroll up?
Yeah.
The CNN. Yeah. So like the way I remember it is that you have like a CNN, right? And you have different filters that like sort of figure out different features of an image. So
yeah,
for example, if I have like a simple like black and white image,
Mhm.
if I apply like a convolution filter over it, I can sort of see what parts of the image are black and white based on that output sort of matrix that you have.
Mhm.
So in that scenario, it's sort of like just it aggregates information together.
Yeah.
But in the filter that you've used, you see that it like it doesn't aggregate stuff, it sort of like predicts sort of things. Like instead of like aggregating my name is to something, it sort of like predicts what's next in the sequence. So yeah, so I was like curious how like those two things are equivalent, if that makes sense.
Well, okay, I'm not saying like this is exactly how it's done. It's just an example of what a 1D vector will look like. So because kernels are usually used like up here, like you said, to predict like where the feature is. But like what if we shrink it to a 1D vector and like scan the input and that will predict it. And this kernel, I'll get more into it later on it in more details. Is that okay?
Yeah, sure.
Yeah, so knowing that this kernel, someone actually made it in a way where if you go back to the slides, like here, you can tell that these multiplication is pretty repetitive. Like you're doing the exact same thing multiple times, you're just changing some like the current state. So what if we somewhat combine it into a 1D vector. So this kernel filter can contain all the equations that we had previously. And then we have another vector of the input. You just multiply them together, and then you get output. Okay? Of course, this won't work exactly. This is like an over idea on like what are the modifications between two and what how can we expand this and improve this. Okay. So knowing this, like, for example, this is how like it'll look like. You'll have a kernel with all the SSM model equations, and you'll parse it one by one through the input and predict the output. So like you see, these are just zeros, so these are nothing. But once it gets to my name, it'll predict is. This will probably move to these three and probably predict Martin, you know? So like it's just like a very simplified version of it, just in 1D vector. So yeah, so these are the two main ways you can do space models. Convolutional with a filter or recurrent, like just doing it how I showed you guys previously. But of course, they both still have their own issues with it. So with that in mind, we can also remember matrix A is very important. That's what contains all the information of the previous states. So with that in mind, I'm just skipping a bunch of these. It's more advanced stuff, just ignore it. Now we can get into MAMBA, which is a selective SSMs. Remember, selective, that's a very important keyword. It selects important information and ignores what's not relevant. So it's breaking into two parts. The selective scan algorithm, which allows models to filter irrelevant information, and the hardware aware algorithm. Because MAMBA is very computational and very expensive, but the guys who made it in a way that it doesn't really affect your GPU and like it runs just as well. So these are the two main benefits of MAMBA. And this is where it gets pretty difficult. I barely understand it, but like enough to like kind of like break it down. So instead of doing the whole thing on one by one, it can be broken into a Mamba block right here. So you have the input and you tokenize it, and you put the input through a Mamba block and it'll output it. So pretty much what the Mamba block looks like is something like this, okay? So you have the input, which like my name is, you once it projects, I assume like you kind of just like separate it, you add that filter on, okay? To select the outer filter on it, and you'll put an activation function, how I mentioned previously. So so like what these two, I'm not too sure how in depth this works, like in Mama block, but like these two will pretty much like kind of filter out what's important and not input and do the active SSM equation. Then you add another activation function, and then you pretty much put it back to the original size, and that will be the output. So this is what goes on it with going through the equation and also selecting what's important or not. So yeah, so there's like a video that he did that pretty much sums it up. Wait, that's not it. I don't know where it is. But yeah, so this block is parsed through every single input. So the same through the whole calculations and getting irrelevant information. We do this Mamba block n times, which is the length of the input sequence, okay? And that's pretty much what Mamba is. And so how is Mamba currently used in the industry right now? It really isn't. That's the thing. Like this just came out in 2023, so it's still new, and like it's being really popularized. Like it's been so popular. Like people are making their own like modifications of it. Like one, I forgot one's called like Jamba. Like I don't know why, like really irrelevant, but like people are making modifications of Mamba, like Jamba or something else. I forgot to like assign to the current workflow. And like back in 2023, there was like an international conference, and this paper, people thought it was going to win, but they actually got rejected, and that caused a lot of controversy within like the machine learning industry. But I know one way we could use this in is of course predicting like language models, because I actually ran Mamba on my laptop. It's kind of difficult because it is mostly used if you have a GPU, but I have a CPU on my MacBook. So it took me like a while to actually get it running. But like I ran Mamba on my laptop, and from Hugging Face, I grabbed GPT-2. I gave it the same exact prompt and I calculated it. And Mamba actually ran, what was it? 4.5 times faster than GPT-2 with the exact same input and just has the best, just with a better response. So that itself shows that this does have potential to replace transformers. Of course, the main issue with it is like just staying good up. There's very limited research on it. If you look up on YouTube Mamba, there's some videos on it, but some of them has like 5,000 views, 1,000 views. So not a lot of people know too much about it, but it's game popularized. And another way this could be used in with an industry is with hedge funds and stock predictions. Okay, the only reason I know about Mamba is because one of my friends who likes quant stuff, he did a project related to this for his internship, and like and because they want to see how can this be implemented within stocks. And I'm not too sure how many hedge funds are actually using this currently, but like it's in the developer right now. And the reason I wanted to do this workshop today is to show you guys, okay, so you guys have a sneak peek of this. So like in 5 years down the line, when Mamba becomes popular, you guys will be like, oh, I know Mamba. Jonathan taught me this 5 years ago. Like you guys knew what it was. It's like knowing what ChatGPT was before it became famous. Okay, it's like a flex. Okay.
It's like knowing the artists before they get popular.
Yeah, pretty much. Like I'm the artist. I'm just kidding. No, 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 no. So Mamba's the artist, Martin, the guy who wrote this paper. But yeah, that's pretty much what Mamba is. I can't go too. Yes.
Kind of confused. I got here in this session, but how is Mamba different than LTSM?
LTSM. Think about Mamba, like I don't know. I didn't look much into LTSM, but I think the main difference between Mamba is like it's a lot faster because they do the computation speed all at once. Okay, and it extracts and distracts information that's relevant or not. Just that's like the main benefits of MAMBA. Of course, there might be more benefits once people start involving doing more research on this. And yeah, that's pretty much all I have. There's a lot more to this, but like honestly, to know all this information in detail, you have to know like a PhD level of like a lot of the mathematical equation. Like, it's very, very complex. So it took me a few hours to like even understand what's going on, you know?
Two questions.
Yeah.
Is the kernel function linear and is Mamba block, like, is it constant time complexity?
Yeah, so the yeah, the kernel. Wait, what was the first question?
Is it like a linear function?
No, yeah, it is. Because for example, like if you ever done like leak code, you want to examine like a like an n by n matrix. Yeah, yeah. So scanning through every single block and see the matrix is n squared. I assume you guys done leak code probably. But for this, you're just running it one time. Okay, so like, the 1D vector will be linear, while the 2D vector of a kernel of an image will be n squared. And what was your second question?
You said there was constant time, right? The Mamba block is constant time.
Yeah, it's constant. It's all constant.
Aren't it's like constant? I think it's like n log n, right? Because the scan operation is like one of many things. So like if you go to like your slides, then you have like multiple matrix operations there, right?
Wait, which one?
Like yeah, go up to like so my bad. is the one with like HT minus one goes to like HT goes to HT goes to
Yeah.
There. So I think as far as I remember, each matrix multiplication with a vector is big of n squared. However, because you're doing this again and again and again, you can parallelize it in such a way that the actual matrix multiplication takes n log n. And the reason why MAMBA is used over like transformers is because transformers have a complexity of O of n squared, while MAMBA has O of n log n, which is faster. That's as much as I know. So it won't be strictly like linear, but it'll be n log n.
Yeah, it won't be exactly linear, but like
Yeah.
the overall idea it is because like in a self-intention mechanism in a transformer, we have an input like on a like chair, it's gonna examine all the information from the previous like input. Why not you see, okay, how much does this chair like impact this input?
Yes.
Of course, self-intention mechanism it's really good, but like once you get to a longer response, it can be very expensive to run. That's why like ChatGPT has like a token limitations on how much you can input before it starts hallucinating. Because hallucination is a pretty big part of LLMs right now. And I think Mamba could really be a way if it's set up correctly and you know what you're doing, it could be really set up where hallucination won't be too much information. Of course, you can't. I believe you can't really always eliminate hallucination, but like you can like decrease it. So I think this will be a very good way. Hopefully, like I said, this just came out 2 years ago. So throughout the years, more researchers do this. It can be improved more and more, and like yeah, and you guys would know about it. Yeah, but yeah, I think that's pretty much all I have for today. I wish I could get more in detail, but like I said, I'm not a big researcher on this, so like I can't explain too much. It's too complex. But yeah.
Thank
Yeah.
you.
Yeah.
Other questions?
And also, if you guys want to look into also